Right, I make it 9 o'clock, so we'll start now. And if we've got any late joiners, they may miss the beginning. The order of the morning will be to go over basic principles of heat pumps, how they work, how they might work in a domestic setting, which applies also to a commercial setting. We'll start with a little bit about us. We'll talk about potential subsidies that are still around and available, running costs, heat pump myths, and then we'll have some questions at the end. We'll also take you through our sort of very basic consulting process that we might use to try and find out which would be more suitable air or ground source heat pumps. So if we start with a little bit about isoenergy, we were founded in 2006. We now have about 60 members of staff. This is split between office staff as well as our own engineering team. So we have, since our conception, since we started, over 1,000 systems installed. So we're pretty well versed. Our target market and our supposed MO is hard to heat buildings. We do everything from consulting, design, install, and we offer maintenance going forwards. Here are some examples of the work that we do. As you can see, that we really started in the industry doing large country homes, manor houses. This is sprawled out to new builds, commercial buildings, schools, hospitals, hotels. There's now not really a building that we won't tackle, but our past with hard to heat buildings has stood us in very good standing when it comes to heating all manners of buildings. So starting with the beginning, we offer a consulting service, so that is over the phone. We'll come out to site, we'll talk to people, we will see what might be best suited to the project and how we might be able to help. We'll look at things such as cost and budget, we'll look at returns, we'll look at efficiency, we'll look at what the existing systems are that we're tying in with. We look at everything as a whole, and we're not tied to any particular part in the market. You'll notice, though, that this talk is concerned only with heat pumps, and that's because there are 3 other seminars following this in the weeks to come that will touch on other products and other solutions. So this one will be focused mainly on heat pumps and ground source heat pumps. We then move to the design stage, so we do all of that in-house as well. We'll provide 3D models, we do all the calculations, we size pumps ourselves. Unless they're integrated in heat pumps, we size pipe work, we do it all. So we have complete ownership of the project from the start to the finish. We then install it all with our own engineers. So again, quality control. We're looking at maintaining a very high standard when we do our installation. So that tends to steer us away from low cost solutions in small terraced houses, for instance, in which there are quite a lot in the UK. But again, we do have some clients that see value in what we do as a whole, rather than just selling a solution. We're looking at providing an engineering solution for the projects that we tackle. And of course, we offer maintenance going forward. So we have our own service engineers, our own maintenance teams, and that's all looked after in-house. I suppose the first question in the beginning would be, why heat pumps? Why renewables in general? But as I said, we're going to focus on heat pumps with this discussion. So why heat pumps? Well, they offer a significant running cost reduction with almost most fossil fuels. The only one that they don't really offer a huge saving against is mains gas, because mains gas is very cheap at the moment. So you're potentially looking at around a 15% to 20% reduction in mains gas, depending on what price you're paying for both gas and electricity, electricity being the primary fuel for a heat pump. You can improve comfort levels in the building whilst maintaining the same level of running costs. Because you offer a fuel saving, you might heat your building rather frugally at the moment, and by lower the running costs, you can have a higher benefit inside the building and an improved comfort level. This can be not just for heating, but also for hot water, as it gives you an opportunity to upsize what might be a pre-existing hot water cylinder that's too small for the requirements of the property. Carbon emissions, again, this varies on fuel, on primary fuel source that you would be replacing. So electricity, direct electricity would be the highest reduction in carbon, as a heat pump is 300 to 400 times more efficient, given its coefficient of performance, than direct electricity. Even mains gas, you will save about 50–55% in carbon, oil around 70% in your carbon emissions, which can tally up to quite a huge amount over the course of a year and over the course of the heat pump life cycle. Future-proofing building for legislation. This comes into play primarily for new builds, as there tends to be a legislation that dictates what they should and shouldn't be doing at the point of building. So they might have a carbon emissions target that they have to meet, or they might have to put in a renewable energy system. Some of our clients start off thinking they'll meet the 10% requirement with PV, and they end up putting in a heat pump because it not only makes financial sense, but it also improves the SAP ratings for their new builds and their energy performance certificates. The last point, I suppose, is the subsidies. So there are current subsidies. There's the RHI, the Renewable Heat Incentive at the moment, and something called the Green Homes Grant, which is an upfront grant, and the RHI is an ongoing subsidy. The RHI at the moment for domestic dwellings is worth 7 years, and there was a non-domestic subsidy available as well, but that ends for new applicants in March, the end of March 31st this year. So unless you're quite a long way down the project, it's unlikely that you will receive that. I see there is a question here from Chris Kemp about losing grant if the heat pump is reversible. If you are using an air source heat pump for cooling, so it's reversible, so it's providing heating in the winter and cooling in the summer, then yes, you're ineligible for the renewable heat incentive because it is deemed by Ofgem as an air conditioning unit rather than a heat pump, a strict heat pump. With ground source, no, you can use it for cooling in the summer and still receive the RHI. And for commercial buildings, if you're doing simultaneous heating and cooling, the way the RHI is structured for those was quite slightly different. So you had to meter off the energy that was produced by the heat pump when you were providing cooling, because it's deemed as a luxury, I think, in the eyes of Ofgem, and not something that they should be paying in terms of carbon offset for. I hope that answers the question. If anyone else has questions, please use the chat function throughout, and if I see it pop up, I will try and answer it. There will be a question section at the end as well. So improved comfort levels, just to explain and elaborate a little bit more on how you get those and what the real benefit is when using a heat pump. You use the thermal mass of the building as a thermal store. So with a conventional fossil fuel system that might be using radiators as a heat emitter, you tend to heat the air inside the building because your heating system isn't on for a very long period of time. That tends to be the standard across the UK. So people might heat their home for an hour or so in the morning, and 3 to 4 to 5 hours in the evening, maybe an hour in the middle of the day. And what you're looking to do is try and heat the air from your radiators, from your boiler. With heat pumps, they're running, and we say 24/7, it isn't 24/7, but they are on and monitoring the temperature inside the building 24 hours a day, and they are trying to maintain that temperature. The benefit of doing this is that the thermal mass of the building, all the internal walls, the floors, the ceilings, everything becomes the internal temperature that you want the house to be. And it's much harder for the house to lose that heat because it isn't just stored in the air, it's stored in the fabric of the building. So you'll find that leaky houses, when you're just heating the air changes might be 2 to 3 to 4 times per hour. So you're getting new air and old air exchanging 3–4 times an hour, which leads to increased heating. That's another question, I believe. Yeah. Oh, yeah, sorry. So by keeping the building at a constant level, it's much better for inhabitants. You find that everything's much more constant, much more temperate. You can adjust the temperature in different rooms. If you have zonal control, you can do that with your thermostats. If you don't, you can balance the radiators using the TRV valves on them to keep the rooms at different temperatures. So you might want your bedroom at 18 or 19 degrees, and you might want your living area at 20 or 21 degrees. It's quite a typical split. It's in listed properties, which of course is what we started doing. It's very good for conservation of items and contents inside the building, woodwork in particular, which doesn't like variance in humidity, and it doesn't like variance in temperature. So you get the colds of maybe 15, 16 degrees of conservation grade heating, and then comfort levels of 21 degrees when you might light a fire or actually put the heating on. It can cause the wood to warp and to crack. So by addressing that, by keeping the building at a solid temperature, you can address that. So another question here from Simon. Regarding hot water, is it possible to boost the tank for an extra hour or two to give guests more hot water? Yes, it is. This is something that I'll touch on just as we get a little bit further on down the line. You can address hot water in two ways, though. One is via a larger volume, and the other is by higher temperature or a boost function through an immersion if you need to. But we'll go on to that a little bit later on. You can see there the last note is hot water and however much you want. Paul, is that better? Just a comment on the volume of the microphone. Okay, there we are. So you'll see there the last point touches on hot water, and you can have plenty of it, as you can with a fossil fuel system, and it will be plenty hot enough. We'll go on to heat pump myth busting at the end. So carbon reductions, as I said, you can exceed 55%, and that would hopefully be the minimum against mains gas as a carbon reduction target for putting in a heat pump system, depending on the fossil fuel you're offsetting. Heating emissions make up about 18% of the UK's total carbon footprint, and so we can address quite a large, almost a fifth or a fourth, a quarter of the UK's heating emissions as properties keep springing up, and as the population grows in the UK, the heating. I mean, new builds will account for a relatively small amount of it because we have quite a large proportion of period housing stock in the UK, and that tends to be where the heat is lost the most because they're less well insulated. A majority of them being listed, of course. Future-proofing buildings, so legislation in the UK. You've got the new Part L regulations that are coming to force, introduction of SAP 10 targets, that's starting in the city. Local planning conditions, they vary from local planning authority to planning authority. Some of them require you to put in a renewable heating system. Some of them say you have to meet a 10%, 20%, 30% carbon reduction target. So it might be that you choose to install a heat pump to offset some of those conditions for planning. There's potential for fossil fuels to be phased out. You look at recent legislation that was announced last year, they're looking at no new homes being connected to the gas grid by 2025. So it means that either they have to do something to remove the gas grid being called the gas grid, and it might be that they start bleeding hydrogen into it, as they are testing throughout the UK in certain areas, and it becomes the hybrid grid, which gets the government around that obstacle. Or they start legislating to put heat pumps as the most appropriate replacement into domestic households. No terrace household could have a biomass boiler installed. You could have a large district heating system installed there, of course, but they do have a better chance of putting in air source heat pumps, which I think is what the government is really hoping that people will start taking on board. You'll see as well that there have been more adverts on the television and on the radio. Companies like Valent, Mitsubishi, they have been pushing the renewable heating agenda quite hard, as well as just their boilers. So hopefully there's more of that in the UK, and they become more of a well-known option with regards to heating and hot water, because I still think that many people, if you talk to them and stop them in the street, wouldn't know what a heat pump is or how it works. So future is electric. You can see that with what the government mandates are with regards to vehicles as well as heating. We're hoping that with new SAP regulations, they favour heat pumps more than direct electric heating, which has been a bit of a stumbling block in the past. If you look at trying to do new energy performance certificates or SAP calculations, heat pumps are weighted very similarly to direct electric heating. Which isn't really right, because heat pumps are more efficient. Yes, they use direct electricity, but you get much more heat out of them than you do from an electric plug-in radiator. And lastly, again, a bit of crystal ball gazing. We're thinking 10 years into the future. It's likely that there will be no fossil fuel boilers in place. There might be exceptions for certain buildings. You know, there are exceptions in terms of insulation, of course, windows and doors and fabric changes for listed buildings, and that may be increased to include fossil fuels, because a lot of them are too far away to upgrade electricity for heat pumps. They might not have access to woodlands for biomass, so they might still be exposed to fuel price fluctuations, and so it might be easier for those buildings to have exemptions, but we don't know. But I would expect that, you know, within 10 years, especially given the social pressures, for people to have to replace fossil fuel heating systems. And of course, just general considerations for renewables and for heat pumps in particular. You would look at which solution is best for the property. Again, we're just touching on heat pumps on this talk, but there are other technologies, and we can talk about those either one-on-one after this, or you can tune into the other seminars. Running costs. So you're looking at perhaps lowering your bills as you're going to stay in the property for the next 20, 30, 40 years. If it's a project that you're looking to stay in for a long period of time. Government incentives, would your system be eligible for any of those at the moment? And social pressure. So we've seen a lot of climate change movement in society, especially recently, the likes of David Attenborough and Greta doing their bit to champion the cause. So I think a lot of people are, we're seeing inquiries coming in and they're saying, I've started thinking about carbon and my footprint, and they'd like to see if there's anything I can do to offset that. So, and more people are becoming aware of their day-to-day carbon emissions and their footprint, and what they might or might not be able to do to reduce that. So, as I say, there's a plethora of technologies. There's solar PV, there's micro hydro, wind, heat pumps, biomass, and that's just a selection. Just got a question here from Daniel Fox. Have there been any more talks regarding non-domestic RHI? No, not that I'm aware of, I'm afraid. It seems as though that if you didn't get a tariff guarantee, or you don't get a tariff guarantee in before March this year, you won't get the non-domestic RHI. Likewise, if you can't apply for a COVID delay extension, so that was for projects that have been started before August 17th last year, and you have proof and there's a list of evidences, again, you can't apply for an extension. So the COVID delay extension gives you an extra 12 months past March this year. But if you can't get the tariff guarantee and you can't get the COVID extension, the non-domestic RHI at the moment is due to end in March this year. Just back to the technology. So there's biomass, you can have chip or pellet. Chip is predominantly more useful where you can produce your own chip. And pellet, of course, you would buy in as a fuel source, compressed sawdust. Heat pumps, which we'll go into in a little bit more detail. Micro hydro wind, so things like water wheels or Archimedes screws. Wind turbines, which are notoriously hard to get planning for. And solar PV. So there's another talk coming on solar PV in the next couple of weeks. And there is another talk on air source heat pumps, and there is another talk more specifically on ground source heat pumps, ground collector designs as well. And I believe that's the next talk after this one, next Friday. So before we get started with heat pumps, how they work and why they're great for providing you with the energy you need, we should talk about reducing the amount of energy that you need. Of course, the most cost-effective unit of heat is the one that you don't have to buy. So if you can remove the amount of energy or a proportion of energy that you're consuming in a year by perhaps moving from single glazing to double glazing, looking at draft proofing where possible, insulation in the walls if they're unfilled cavities, or in the attic, indeed, if you haven't got any loft insulation, then you can reduce, sometimes quite significantly, the amount of energy that a building requires. So we have looked at projects in the past where just by replacing all the windows, they could save 20% of the energy that the building is losing, which is quite a huge amount. They could then save a further 15% with insulation in certain areas. So that's a 35% reduction in the amount of energy required before they even looked at reducing the running costs of that system. So we would recommend, before you even look at anything, is there anything that you can do in terms of insulation for the building? If not, then you're looking at, you may have made all of those changes or alterations already. Then we're looking at how can you provide that unit of energy, the amount of energy that you need over a year, most cost effectively. Doing that. Oh, we've got a question here from Jordan. In terms of insulation, what's the most environmentally friendly material while still being effective? We've seen quite a few different materials going into buildings. I have seen on products that I've worked on hemp, which has been sprayed onto the buildings, and that of course really works for new builds where you've got exposed walls and you're able to put that in. Straw has been used before. Wool, you can get big rollout sheets of wool that will replace fiberglass insulation in buildings. So in terms of effectiveness, there's also spray on foam, which I think seals a building quite well, but it can lead to sweating in certain instances, depending on how the rest of the build is going. So it really depends on what sort of building it is you're looking, whether it's a new build or it's an existing building. If you want more advice on that, we can have a chat afterwards. So reducing running costs, how best to do that with a heat pump? How does a heat pump work? What is a heat pump? You can see here there's a range in the images of heat pumps. This is one of a few manufacturers that we work with. This is a manufacturer called CTC. They have air source heat pumps in the range, which are the air conditioning looking units at the front. And they generate the heat at source. So they have the compressor inside and they then send that heat to a heating buffer tank and a hot water cylinder. You can combine the two. In the CTC range, you see behind in the middle, they have a cylinder sized unit, and that is providing hot water on demand, much like a combi boiler does, and it is a heating buffer tank itself. You can tie in solar thermal and things like that. It's quite a neat solution where space might be tight, and it has the controller built into it. Standard heat pumps look very similar to a fridge, either under counter, as you can see on the far right-hand side, or fridge freezers for larger units. And you may need 1, 2, 3, 4 of them, depending on all sorts of factors, size of property, and heat demand are, of course, the driving forces for that. What a heat pump is doing is it's using electricity to amplify ambient energy that's found in the environment. And it can be taken from a series of sources. So air source, of course, taking energy from the air. Ground source, name almost a bit of a misnomer, takes energy from anything in the ground. And it can be groundwater, it can be running water, it can be underground water in the aquifers via boreholes. You could be pumping water out of the ground through an open loop borehole system. It could be horizontal pipe work buried in the ground if you have paddocks or fields. So there's many different ways that the heat pump can take energy out of the environment, which will be covered in the seminar next week. But we'll go through a few of them today, just touch on them briefly. Your source temperature starts off, of course, very low. Your environmental temperature, and like for air, for instance, fluctuates quite dramatically throughout the year. Of course, you can have 25, 30 degree air in the summer, and you might have -5 degree air in the winter. So there's a huge variance in the energy that's supplied to the system, and how the heat pump has to deal with it. Of course, most properties in the UK actually have a heat pump installed already, and it's probably quite a common method of comparison is likening a heat pump to a fridge. And you will see here, this is how the fridge works, and you'll see on the next slide that it is almost identical with how a heat pump works. So you have a compressor at the bottom there of the fridge, which is heating up a liquid, running out through an evaporator on the back, and then through an expansion valve where the liquid cools down dramatically. You run that cold liquid through the fridge, which is cooling it, and the process repeats itself. It's slightly more simplified, but that's in essence what's happening with a heat pump, just in reverse. So you've got the heating element that's on the outside of the fridge, actually inside the building, which is your radiator circuit or underfloor heating. and the cooling section of that outside in the field. So here on this diagram, you can see exactly how that's working. You start off with section number 1. So on the image, location number 1 is the collector array, what we call the brine pipework in the industry, connected to the heat pump system. So you've got incoming brine, which is a glycol water solution, running through the system over a heat exchanger, which is being used to evaporate a refrigerant. And that refrigerant boils at about -20 roughly, and your source temperature is about 10 degrees roughly. So although it isn't hot, it's relatively boiling to that refrigerant. Now, once you have boiled that refrigerant, you've created a gas, and it's a slightly warmer gas than it was when it started off as a liquid. And you run that through item number 3, which is the compressor. It's an electrical compressor. Now, that's where your electricity demand, and you have a few small circulating pumps as well, but that is the bulk of your electricity demand when it comes to running a heat pump system. So you're using that compressor to condense that gas, and you're condensing it back into a liquid. Now, we're generating temperatures of around 65 degrees at that compressor, 60 to 65 degrees. There are manufacturers that do high temperature heat pumps where you can get 70, 75 degrees out of them at the flow end for usable heat. And some of them go even higher for process heating at the cost of efficiency and size. So in a domestic scenario, you would look to be achieving 60 to 65 degrees at point number 3, which is in the compressor. Once you've got that condensed gas, which is now liquid again, you run that through a heat exchanger, second heat exchanger, which is section number 4. And it is, when it's going through there, it's losing heat and being absorbed through another heat exchanger, which is feeding heating and energy onto your heating and hot water circuits. So that is taking energy from that 60, 65 degree liquid that you've created and passing it over to your heating and hot water circuits. As you move down towards number 6 at the bottom, that's the expansion valve, where the liquid is forced through the expansion valve, turned into a gas again, and cooled down rapidly. The process then starts again. So you're using electricity to phase change, or the environmental energy and electricity to phase change a material, which is in a closed circuit. And by doing that, you're generating the high grade and low grade heats, the high grade heats from low grade heats that you need for your building. So that very roughly is how a heat pump is working, and it's doing that process. It's carrying out that process all the time that it's running, and you can hear it running. And it might be for 10 to 12 hours a day, but because the running costs are less, then it's costing you less energy. We have another question here. This is from Paul. Can you provide a top 10 or 5 aspects to consider and install in a new build float concept foundation, underfloor heating? It's a relatively long one, Paul. Do you mind if we come back to that at the end? And if it's more specific to a project that you're working on, perhaps you can contact me separately for that one. Thank you. So heat pump efficiency, how it works, and the proportions of electricity versus your environmental or source energy that you're getting, you can see here in this very basic pie graph. You've got electricity accounting for 1/4 of the energy that is supplied as a whole to the property. So if you have 4 units, 4/4 of energy, the other 3, the remaining 3, will come from the environment or your source energy. So you end up with an efficiency of 4 units of heat out for 1 unit of energy going in to the system. So that's how you get your COP, the coefficient of performance of a heat pump, and why they're so much more cost effective to run. Here you can just see a table, very roughly. It shows running costs. Mains gas and heat pumps tend to be the most common comparison, as there's most amount of homes on the gas grid in the UK. And then you've got LPG, which is slightly more expensive, more expensive than mains gas, slightly less expensive than oil, and direct electricity being the most expensive heating source for the UK at the moment. And it might be that they do something to incentivize the running costs of electricity, which would be great for heat pumps as well, because of course they're running on electricity. But that shows you very roughly how air source and ground source stack up in terms of heat pump running costs with other units of heat. And the renewable heat incentive, as you saw in the pie chart, there was a little key that said the renewable heat incentive, the subsidies are paid on the renewable portions of the energy. So it's effectively a carbon offset payment at the moment, and it's running until March 2022, next year. For domestic properties, as I said, the non-domestic subsidy is pretty well ended now, and you have to be very far along your project to even consider getting it. So we're not going to talk about that. It's a 7-year scheme, the domestic subsidy, and those are the unit rates for each of them. They're linked to CPI, so they go up with consumer price index inflation each year, roughly about 2%, and they're paid tax-free in most cases. They're available to domestic clients. So if you're a self-build for a new builder, or if it's a heat pump for a retrofit that you own, even if you tenant it out, developers are unable to receive this subsidy as they're selling the home afterwards. So they would put the system in and they wouldn't receive the subsidy for it. For heat pumps, ground source heat pumps, it's worth about £4,500, £4,600 per annum for the 7 years. So it's just shy of £30,000 back at the end of the term. The actual amount that you receive is based on the amount of energy that's required by the property, and that is shown on the energy performance certificate. Conversely, you're actually paid more for having a worse energy performance certificate and a higher amount of energy required. And that's because it's a carbon offset payment. So you are offsetting more carbon, so you receive more benefit. They're also assuming that because your house will be less well insulated, the system will cost more, and therefore you should get more subsidy. So it's not a benefit for having the most environmentally friendly house on the planet, sadly. It's a benefit for reducing the amount of carbon you're putting into the property. Solar thermal is about £200 per annum. Air source heat pumps about £1,500 per year, and biomass about £1,600 for domestic dwellings. Right, so heat pumps, just to recap, they're taking energy from the environment, any environmental energy source. We're doing a project in Bath for Bath Abbey, where we're taking energy from the Roman drains, the hot springs, which is coming out of the ground at about 40 degrees. So that system should be very efficient, but it just goes to show that you really can take energy from anywhere with the correct design. You are using a heat pump to create around 4 kilowatts of heat for use in the building for every 1 kilowatt of electricity that they use. So that's your source energy from the environment, accounting for the rest of that heat that is being produced into the building. You're looking at a typical running cost reduction of 40 to 75%, depending on the displaced fuel, and around 20% now since I wrote this for mains gas. So I would say that if you're looking at mains gas, your fuel saving is going to be much less than it would be if you're displacing oil. They're just as capable of heating any sort of building with the correct design, and actually the heat emitters inside the building. So again, we'll touch on that towards the end, where we go through a bit of myth busting with heat pumps. They work well with both radiators and underfloor heating. Your radiators do have to be slightly oversized in some instances. You tend to find in the UK that they can be oversized already. And one of the greatest benefits of heat pumps is you're not withholding to any fuel deliveries anymore if you are buying in fuel. So if you're on LPG or oil, you'll feel much more like you're on a mains gas system where you're just on a main supply, because the heat pump is running on electricity. So you're not withholden to fluctuating prices so much, because you're only using a quarter of that incoming cost to run the system, and you don't need to worry about fuel deliveries anymore. So ground source heat pumps, here's a little infographic that shows you, probably the 3 most common collector types for them. It's pipework closed loop in the water, and you need multiples of pipe collectors depending on the size of the system. Closed loop boreholes, so that's again vertical system of pipework buried in the ground, and you're drilling boreholes anywhere from 100 to 250 meters, sometimes deeper, sometimes shallower. You get about 4 kilowatts of heat out of each 150, 140 meter borehole. So again, depending on how large the system is, depend on how many boreholes you need. And horizontal pipe work laid out, not quite like it's shown just there, but close enough. And again, we're probably looking, I would say, on the smallest end of where you might put in the ground source heat pump, about half to 0.8 of an acre. And the largest system we've done for a domestic ground source system was 10 acres. So it really does vary on the size of the system required. This is the single biggest mistake, and my colleague next week will go into more detail on this when he's talking about collectors for ground source heat pumps. But it's coiling pipe work on the right hand side versus how you should install pipe work on the left hand side, which is a single run of pipe looped back on itself. The reason, if you look at the cross section of that from a bird's eye view, is that you have 4 times more pipe work in the coiled version per square meter of earth. Now that's fantastic if you're in the water, because water is moving, there's convection currents and energy moves more freely. So you're able to take a lot more energy out than you are out of the ground. In the ground, however, energy moves very slowly. So you need to make sure you're limiting the amount of energy you take out per square meter to what the earth can provide back into the ground in that local geology or soil type. So you'll find that in bone dry chalk, it drains very well. So water percolates through, which is fantastic, but it doesn't retain heat very well because there's no moisture in it. It doesn't absorb very well. Likewise with sand, it's a very good insulator. So once you have covered the pipework in sand back over in a sandy soil, you need to make sure that you're able to take enough energy out and that your recharge will be significant enough for you to be able to keep extracting at the rates that you need to. So it all comes down to correct design with your ground source heat pump system. At the head of each trench, we've got a question from Darren. Is there an allowance to make when sizing ground loop array when working with ground source intended for both heating and cooling? So this question from Daniel relates to how do you size a system when it comes to cooling and heating. Yes, you tend to find that you need a smaller collector array when you're doing cooling because you're dumping heat in the summer into the ground. So there is an allowance that you need to make, and like with all of these systems, it's on a case-by-case basis. You can't just say, well, we're going to take out 30 watts a meter as opposed to 12 watts a meter. So there's no rule of thumb, but there is an allowance that you make, and it does have an effect on the overall collector size, yes. So here on this screen, you can see at the head of our collector arrays, we have a manifold, and it looks just like a giant underfloor heating manifold on the inside, and then each of the pipes goes off to a trench. Now we have our meter wide trenches with the pipe work in, then a 3 to 4 meter gap between each. Thermally, you need a minimum of 2.5 meters between each trench. We use 3 to 4 because it's easier for the excavator to get between them, put the topsoil on one side and spoil on the other. So it's partly for ease of digging, but also because it offers a better result in terms of ongoing efficiency. Here you can see a typical one of our projects, a large property, large country house, 45 kilowatt heat load for about a 750 square meter house. We need about 2 acres of collector, and there's a tennis court there that shows you to scale roughly how much land there is. There's no rule of thumb again for area of property. It's not half an acre for every 200 square meters of house. It doesn't work like that. It really relates. It's very bespoke sizing for ground collectors because the geology in the UK is so varied. Here we're looking at about 14 100 meter long trenches. That's 1 meter wide by 1 meter deep by 100 meters long. And each 100 meter long trench has a 200 meter loop inside it because of course it doubles back on itself. At the head of this array, we would have 2 manifolds like we showed in the picture. So here you can see we've got a question here from Paul. I understand that systems that cool and heat are not as efficient as heat only. Why is this? I don't think that's necessarily correct. You'll find that the heat that's dumped into a ground array during the summer will actually increase the temperature of that ground array for the winter. It doesn't work like a heat battery. The energy does move quite quickly through the earth, but it does help improve the flow temperature of the heat pump. It depends how much you're heating the pipework back up to, and that again comes down to the correct design. Because yes, you can dump heat into the collector array, but that source temperature, your glycol brine inside the collector, will stop the heat pump running if it exceeds 20 degrees. So if you're dumping too much heat into it and you heat that glycol up to about 30 degrees, then the heat pump won't work. So that might be the sort of thing that you're touching on. But again, it's all very, very bespoke when it comes to these sorts of things. Robert, we've got a question from Robert Archer. Is it better to have the pipes buried deeper than a metre, more heat deeper down? No, there's no benefit to going any deeper than a metre. Below 1.2 or 1.5 metres, you have to shutter the trenches, which leads to exorbitant costs, and there's next to no thermal benefit. We're not actually looking for geothermal heat. What we're looking for is, well, what we're hoping for is solar gain. So we're looking for sun beating down on the earth and warming it up, and we're looking for the sun warming up water in the clouds, which then turns into rain, which falls down and percolates through the soil and warms up our pipework. So although we call it a ground source heat pump and everybody bangs on about geothermal energy, the only geothermal heat pumps are, as I mentioned, the one in Bath, which is taking energy from a geothermal reservoir of water under the city, or where you've got very deep boreholes. And I know there's a scheme down in Cornwall where they've got a 1 kilometre deep borehole or something, which is going for true geothermal energy. Of course, other geologies in other countries will be able to do that. But in short, no, there's no benefit to going any deeper. In fact, it might make things worse because horizontal collector arrays are looking for solar gain of some sort, rainfall or direct sunlight. This image here shows two comparably sized systems in two different paddocks. So the right-hand paddock, the darker paddock, you can see some very faint lines going up and down, and that is our collector array 12 months on from the system on the left-hand side, which you can see has just been installed and has left scars on the land. So once the heat pump system goes in, it should be invisible, of course, apart from satellite imagery, but from the ground, you probably wouldn't know that it was there. Boreholes, so this is another potential energy source. You can have open loop or closed loop. A colleague of mine next week will go into these in more detail. But again, it's doing exactly the same job as the horizontal collector. It's slightly more efficient. You're able to take more energy out because you're looking for the aquifer. That's our energy source here. And so what we're looking for is high levels of groundwater. You want it to be as high to the top of the borehole as possible, so as much of your collector is submerged as possible. Water source, again, this is ground source because it isn't open loop. It's not pumping water out. It's water that is on the ground. It's groundwater. So this is a ground source system. These are called energy blades, and as water rushes over them in flowing bodies of water, they can absorb that energy into the glycol that's inside them and transport that back to the heat pump system. So each energy blade is about 3 meters long by 600 by 600 in cross section, and you get about 20 kilowatts of heat out in good running water. So they are a very efficient way of taking energy out of water or the environment for a heat pump, and because they're so efficient, they're a low running cost because you don't have to go digging up huge amounts of land, and they're fine just in rivers, as you can see on the right hand side there. Lake loops, again, it's ground. This is ground source. It isn't water source. It's true water source because you're not pumping water out. We've got collectors of coiled pipework, and as I said, when you're in the water, you've got convection currents. So it's much easier for that energy to be dissipated into the environment and for fresh relative heat to come into contact with the collector pipework. So it's okay to coil your pipework in water, especially when there is movement. This pipework will sink. It won't stay on the top once it's buoyant at the moment because it's full of air. Once we fill it full of glycol, the weights on it, it'll become negatively buoyant and it'll sink down to the bottom and will silt up over time. So that's water source. And when it all goes wrong, so a lot of people, again, we'll touch on this at the end with myth busting, are worried about the ground freezing. And again, that is a symptom, it's symptomatic of poor design. You should have heat pump systems that have a 20-year lifespan in mind with design. And if they're lasting 20 years, there's no reason why they shouldn't go on to last 50 to 100 years. What we're looking to do in terms of temperatures in the ground is take out about 3 degrees. So that's the delta T, the difference between our outgoing brine temperature going out into the collector and the incoming. We're looking to harvest 3 degrees from the ground. Now, if you reduce the amount of area that you're taking energy from, then you will increase the amount of temperature deficit, the difference, the delta T, in that localized area. And by increasing that temperature, you're taking out more energy, and then it will start dropping. So if you're taking out 3 degrees per year, there's 100% chance that that energy will recover over the summer as the ground temperature goes from 8 degrees in the winter to 16 degrees or so in the summer. Just a question for Jack, what type of glycol do you use for water source array? Does it need to be polypropylene? We use a vegetable-based glycol. So it's a non-notifiable, non-toxic liquid. So if it leaks, it will just biodegrade and not cause any harm to any wildlife. That's just part of our ethos and part of the whole reason that we're doing this. The glycol, because it breaks down, because it's vegetable-based, it has a lifetime of about 20 to 30 years. So you'll tend to find that you have to flush the system out to do that. Chris, do you look to reverse heat pumps to recharge the ground or rely on the solar input? You should rely on the solar input. As I say, when you're looking at cooling and dumping heat into the ground, you can't rely on that because you might have a very mild summer where it's not that hot and you don't need that much cooling. So if you're relying on putting 20% of the energy or 30% of the energy back into the ground and you don't actually do that because you're not cooling with the system, then you're going to be a bit of a sticky wicket for the coming winter where your ground temperature starts off lower. So just going back to this. So what you're looking to do is take as little energy, I know it sounds ridiculous, but take as little energy as possible over as larger area as possible, because it is, at the end of the day, the environment that you're relying on for your energy source. You will hear people saying, yes, of course, in your quarter of an acre garden, you could put in 1,000 meters of pipe. Of course, you can physically fit it in, and yes, it is a cheaper solution, but it will fail potentially after a year as the ground gets progressively colder, and the next year it then freezes. So again, key design. Heat pump plant rooms. This is something that's often underestimated and becomes a real trouble for us when it comes to new builds, because they've never really been factored in. They think, oh, well, we've got the utility room where the boiler is going to go. Can the heat pump go in there? No, is the short answer. So this is a typical heat pump plant room. You can see here we've got this is a 14 kilowatt heat pump on the left-hand side. It's a small unit, like an under-counter fridge size. You then have a hot water cylinder, which is the larger of those two tanks at the back of the room, and a heating buffer cylinder just to the right of that, small expansion vessel on the floor, and then the pipework throughout. Now, your hot water cylinder is larger because your hot water storage temperature is lower. So when you're having a shower or a bath, you mix in less direct cold water and you use more direct hot water. So that's why you need to have a larger storage capacity than you would traditionally. In a typical domestic home in the UK, you might have a hot water cylinder that's more akin to the size of that heating buffer cylinder. So that shows you a comparison between what you probably have for your hot water currently versus what you should have with a heat pump. Now, there are all sorts of heat pumps. Some have built-in hot water cylinders. They are better suited to properties where there's one bathroom. So the only use could be one shower at a time. And you can get heat pumps, and as I said, CPC have a solution that does instantaneous hot water, much like a combi boiler. Again, only really suitable for single bathroom households where you might be having a shower and run hot water for washing up currently. So this is a relatively small system. I would say this is for a 100 meter renovation property to a 200 square meter new build. This is the sort of size of system that you would be required. This is a slightly larger system, next size up. It's a 20 kilowatt scheme. So you're looking at a sort of 400 square meter new build or a 200 square meter retrofit. And again, you've got the 2 cylinders and the heat pump. The heating buffer vessel, just touch on that, is crucial because you need to give your heat pump a large heating target to get it running for as long as possible. So we like to limit the amount of starts in the compressor inside the heat pump, because that is the highest wear and tear on the system and the most expensive bit to change. And by starting it up constantly, you wear it down faster. So to give the heat pump a longer period of running, so it's starting less and just running consistently, we give it a larger target to point at. So you've got your heating circuit and the volume inside that, and we add a buffer vessel onto that. Not only does it provide a bigger source, the target for the heat pump to be providing energy to, it also gives us a good point to monitor the system. So the heat pump, in terms of control, is looking at that temperature of the cylinder and monitoring that constantly. If it starts dropping, it will ramp itself up and provide a higher temperature because it recognizes the house requires more temperature. And if it's sitting at temperature, it'll then shut off because it recognizes there's no draw on the house circuit side. So that's why you need a heating buffer tank as well. And again, there are systems that have built-in buffer tanks that do instantaneous hot water, but this is a sort of system that you would have if space is not too much of an issue. This is a slightly larger system. This is about 70 kilowatts worth of heat. I appreciate there's no scale on the cylinders, but they are, again, significantly bigger. And the heat pump itself is much bigger. That heat pump is about 1 meter square or 1 meter cubed in footprint, and the cylinders are about 2.5 meters tall, so quite large. And this is something you might see in sort of a large stately home or a country estate. We've got 3 very big heat pumps here. This is a manufacturer called Viessmann, and this system is doing heating only. So you'll see at the end of the room, behind the heat pumps, is a big buffer tank. The systems, these heat pumps are probably, again, 1.2, 1.3 meters cubed, so they're very big. And we're given an external garage to use as the plant room there. This is a design sort of similar to the last picture I showed you. It's just without the 3rd heat pump. So again, this is quite a large scheme, but you can see the amount of space required between each system, each bit of equipment either, and location of items. We like to plumb from cold to hot, so we would have our brine pipe work coming in near to the heat pump, so you can see it over on this edge, and then we plumb it into the heat pump. Then as we move towards the distribution, which is the bottom right-hand corner of that plant room, we're plumbing to hot, so heating and hot water, heating buffer tank, hot water cylinder, and then we exit the building and provide heat out through those pre-insulated pipes to the target. This is a 3D view of that plant room, so you can see you've got the heat pumps there, cylinders there, and those heat pumps are about 1.3 meters tall. The cylinder is about half that again, or 100% of that again. So they're twice the height of the heat pump. So you're looking at about almost 3 meters in terms of cylinders. This is a large system, but it gives you an idea of how big these systems can get. It's probably for I would say, 90 kilowatt load, about an 800 square meter big country home. So just walking you through our consultation process very briefly, and how we get to the point where we decide what it is that you need on an individual project basis. We're looking at the gross internal area. So it might be a 200 square meter new build. We're looking at the watts per square meter. So that's the amount of energy that building is going to need at -4. We use as an arbitrary figure for the winter temperatures. And we're looking, that gives us a total heat load. So if it's a 100 square meter new build, you're looking at maybe 40 watts a meter, maybe 30 watts a meter. So it's going to be between a 3 and 4 kilowatt heat load. Double that for a 200. So you're looking at about 8 to 6 kilowatt heat load for 200 square meter new build. Then hot water requirements. So what do you need? Are you having big rainforest shower heads with a high 45 litre a minute draw, or are you having showers over baths, 9 litres a minute? And how big are the baths? How much hot water do you need? You look at the most appropriate technology. As I say, that it's not just heat pumps, but in this instance, we would look at which heat pump is best for you. If it is the one bedroom, an apartment or a flat above a stable block or something, or a terraced house, you would have a heat pump that has built-in hot water cylinder potentially to limit the amount of space required. And you might have built-in buffer tank with hot water produced on demand. So there's all sorts of different solutions for different projects. You look at appropriate manufacturer. Again, we're not tied, so we're whole of market. We're looking at which solution best suits clients and end users with their requirements. Fuel savings, what are you offsetting against? If it is a new build, how far away is the gas grid? Is that even an option? Would it be oil as an alternative or LPG? Are there any subsidies available for that particular project? Retrofit, new build, is it the grants? Is it the subsidy which would better suit that model, that economic model for that project? And of course, carbon savings, what's available to you? And again, that is what are you offsetting against as an alternative fuel source? Typical system sizings. So this is something that often people ask us is, what sort of property have I got? I would say that heat pumps really start at this, in real effectiveness around 150 square meters worth of building. Any lower than that, and it's very hard to find a cost-effective solution, you would probably look at an air source system of some sort. But again, with properties much smaller than that, you tend to find it's quite hard to find the space required to put in those systems. So a sacrifice has to be made somewhere. Our typical projects probably start around 250 square meter. So you've got new build there. You might need 7 kilowatts. That's between the 6 and the 8 that we were talking about for that size property. So you put in a 14 kilowatt air source heat pump because the source temperature in the winter is much cooler. That's your air temperature. So your heat pump has to work harder. So the output is lower than you would think. So it's, yes, badged at 14 kilowatts, but actually it's only going to give you about 9 or 8 kilowatts in the winter. So that's why you have to oversize your air source. A colleague of mine will go into more detail on that in the coming weeks. I've just got a question here from Paul Clark. Images of plant rooms are larger than expected. What's the approx plant room size required for a 4 or 5 bedroom house? Is this 3-phase supply required? So a 4 to 5 bedroom house, you're probably looking at 250 square meters, I would say. So if you look, and it's a retrofit renovation, then you're looking at a 14 kilowatt requirement. So I would say for ground source, it's probably looking at about 3 to 3.5 meters along one wall, and we would like 1.5 meters off that wall. So if you, depending on where the doors are and accessibility. So if you've got 3.5 meters by 1.5 meters, that's the sort of space required for that sort of size house. 3-phase, no, you wouldn't need 3-phase for that system. With a ground source heat pump, you can supply up to 22 to 24 kilowatts on a single phase supply shared with the house. With air source, you can get up to about 18 kilowatts, and that would be with 2 air source heat pumps. It would be 2 single phase 16 kilowatt air source heat pumps, each of which gives you about 10 kilowatts. So you're around the 18 to 20 kilowatt mark on a dedicated single phase. Above those levels, so depending on how well insulated the house is, how much energy it needs, you would need a 3-phase electricity supply, yes. And then just going through the other system sizings, you can see 400 square meter new build, of course, is bigger, so the heat requirement is larger, so you have to put in slightly larger system on the both part. With ground source, you can size the rated output more closely to the required output because there's no fall off in output as the temperature in the winter drops outside, because you're not bound to the air temperature, you're bound to the ground temperature, which is much more constant. Whereas the air source, of course, air temperature in the winter could be -3, -4. So it's having to work harder, its output is lower. So you have to oversize your air source heat pumps. And by doing that, you look at the data sheets and see what their output is providing you during the winter. And that's what you would size it to. We had a question here from Jonathan. How much higher demand is needed for hard to heat timber frame listed buildings? I'm afraid, again, that's completely specific. So perhaps you could just get in touch with me at the end, either by phone call. But in terms of watts per meter, you might find timber frame Tudor building is 100 watts per square meter of house in terms of heat loss, versus a new build, which would be around 30 watts. So you're looking at 3 to 4 times more heat lost in old leaky listed buildings. Really does the project though. So if you want a bit more detail, please feel free to get in touch afterwards. Renovation buildings, existing buildings, 200 square meters. You can see that heat load is vaguely similar to a 400 square meter new build. So similar in size to heat pump systems. And for a larger renovation or existing building, that's where you top out at about 400 square meters to what's eligible for a single phase solution. So that goes back to your question. You're looking at about 22 kilowatts heat load required, and that would be the limit to what a single phase heat pump could do. Just had a question from Mark. Could you cascade 2 or 3 22 kilowatt heat pumps for a single phase for larger houses? Yes, you can. We have done that before. We would need a dedicated single phase supply for that, because you couldn't share that much current draw on a shared 100 amp supply with the house, depending on what's going on in the house as well. You might have a car charger, which is 20 amps. Your heat pumps will be 20 amps each. So that's 60 amps already. And then you've got your ovens, your washing machines, your kettles. And as soon as you turn those on, you might start tripping the supply. So you can put larger heat pump systems on single phase supplies, but they need to be looked at quite closely. And there's benefits to inverter driven heat pumps as well, of which there are a few manufacturers in the UK which can be limited in terms of output. So they will never draw in excess of what the supply can provide. Myth busting on heat pumps. So this goes back to a few earlier questions that people had, specifically on hot water temperatures. But starting, the first one is radiators, heat pumps and radiators. Heat pumps do not work with conventional radiator systems, which I'm afraid is false, completely untrue. Heat pumps don't work with undersized radiators, but nothing works with an undersized radiator system. So you might find that in an existing property, there are rooms which are cold. They have 1, maybe 2 radiators in, but they are cold rooms. And that's because the radiators are undersized. It's got nothing to do with the source temperature, because you may have a boiler in there at the moment that's providing 70 degrees to those radiators, but they just aren't large enough to provide enough heat into that space. So it all comes down to sizing of the heat emitters. Yes, if they're undersized currently and you're providing 70 degrees, once you start providing 55 degrees, they might need to be even larger than they would otherwise need to be, but they won't be so large that all walls in all houses are covered by radiators. Indeed, it's been quite surprising, some of the properties that we've worked on with their radiators. We've done some listed churches, medieval churches with radiator circuits, where there is no chance to insulate those buildings at all. And they are nice and warm inside. Likewise, a lot of National Trust properties and just the general population of houses and projects that we've worked on are very poorly insulated and running with radiator circuits. So it comes down to the specific design of those radiators, how big they are currently, which you establish with a heat loss survey, versus how much energy each room requires on a room by room basis. So if you take a typical living room, it might be a 2 kilowatt room. And you might have 2 kilowatts worth of radiator in it currently. That would need to be oversized by perhaps 20% if you were putting in a heat pump system to cater to the lower flow temperature. However, you might find that your radiators in your living room are already oversized, in that your building, your room can get too hot. If you unthrottle the radiators with the valves and your boiler's running at maximum, does the room get too hot? If it gets too hot, it means that the radiators are oversized because they're putting too much heat into the building. So by putting a lower flow temperature in from a heat pump, actually you might find that they're perfect. So you can establish that via a heat loss survey, which is what everybody should do as part of a project when putting in a heat pump. But there's no reason why heat pumps don't work with radiators. Just had a question here from Chris Kemp. Or could you look at fan-assisted RADs on new build? You could look at fan-assisted RADs on a new build, but there's no reason why they need to be fan-assisted. Traditional radiators, if they're just double thin Stel RADs, or if they're cast iron radiators, will work perfectly well with a heat pump, as long as they're designed to run with those flow temperatures. You'll find, in fact, that radiator manufacturers give you the outputs of the radiators with heat pump flow temperatures on their websites, on the data sheets. So they are designed to work with those systems. They just need to be sized appropriately. Fan assisted, of course, can keep the sizing down, but it won't be so much more that it's less hassle to wire in the radiators for the fans. So I would suggest that you just size the radiators, and I think you would be surprised at how small they actually are, even though you're working with heat pump flow temperatures. Hot water temperatures. You will find that with most modern showers, they have a mixer bar on them, and that there's a little button on that mixer bar that you click in to turn the shower head a little further and make it even hotter. That mixer bar click button is set at about 38 degrees. It doesn't sound very hot, and that's why you might want it slightly hotter than that. But 38 degrees is a perfectly acceptable shower temperature. Most hotels are limiting, and schools are limiting to 38 degrees for hot water coming out of showers. For safety reasons and also for keeping costs down. Heat pumps can provide you 55 to 58 degrees hot water, and as I said, there are high temperature heat pumps that can provide you even more, but you would expect a storage temperature of 55 to 58 degrees in your hot water cylinder, which as a temperature is too hot to hold your hand under. So it is very hot. You can have very hot water with a heat pump coming out of your taps if you want it. Most of our clients store their hot water around 50 degrees because they want to keep the running costs down, and they find that 50 degrees is plenty hot enough for all of their demands. Some of them even lower. When it comes to safe temperatures and Legionnaires, you take the temperature of the tank up to as high as it will go with a heat pump once per week, that being hopefully 55, 58 degrees, depending on coil sizes, heat pump outputs, and all sorts of things. And then you boost that with an immersion heater inside the cylinder, and that will run typically for an hour or two once a week. If it's a 3 kilowatt immersion, you're looking at around a 45 pence per hour running cost. So it might cost you 90p per week to pasteurize the cylinder for Legionnaires, just to keep it safe. Outside temperature consideration. So you want to look at whether or not the system will be capable of heating the building when it gets very cold outside. We design our systems to provide each building, whatever they're heating, with enough energy to keep it at 21 degrees inside at -4 degrees outside. So that's our winter design temperature that we work to. CIBSE building design guidelines are normally around -2.5. So we try and exceed that just to provide a little bit of a larger level of comfort. But all of our systems are designed to heat the houses in the winter, and they do exactly that. So there's no reason why, when it gets very cold outside, your heat pump shouldn't be heating your property inside. If it isn't, either your radiators are undersized, your heat emitters are undersized, and no one's taken that into account, or the heat pump system itself is undersized. But if it's been designed correctly, there's no reason why, when it gets very, very cold, the heat pump shouldn't heat a property. Running costs. A lot of people are very worried about high running costs. Again, this tends to be a design flaw if your heat pump system is running quite highly. A few years ago now, we rectified a system that was installed by another company where there was one less borehole put into the ground than required. And it was a small system, so it made a real difference. It was a 12 kilowatt heat pump with two very shallow boreholes when 80 meters each, where in fact it needed a third. So it was 30% less undersized on its ground array, which led to a running cost of about £6,000 a year with a heat pump. When we put in that third borehole, and we replumbed the system as well to make it more efficient because the hot water never got up to temperature, the running cost dropped down to £1,200 a year. And it was so high because the boreholes had actually frozen. So the brine temperature coming into the heat pump was -9. The heat pump was cutting out because that temperature is too cold for it to provide a safe running operation. And so it was calling in its electrical inline heater as a backup. So the house was effectively running on direct electric heating, even when the heat pump was running, because the source temperature was so cold. It wasn't designed to do that. And so it was costing 5 times more than it should have done, because that's the cost saving that you receive when you put a heat pump in versus running on direct electricity. It's about 70% less. So running costs shouldn't be high if your system has been designed correctly and installed correctly. Then you should meet the targets set out in, hopefully you've had cost benefit analyses and proposals, financial models done for you. And the last one is ground conditions. Everybody's very worried that certain ground conditions wouldn't work with heat pumps. So people say, oh, you know, I'm on chalk or I'm on sand. I understand that the heat pump system, we couldn't have a horizontal ground source heat pump because it just won't work. Again, that's incorrect. You just need to size the collector to the geology. So you might be able to take 12 watts per meter out in bone dry chalk and in clay, which is a much more moist thermal conductor. So it's got a higher transfer of energy rate. You might be able to take out 16 to 18 watts per meter. In water, as I said, you can take out potentially 30 watts a meter, boreholes 28 watts per meter. So it's looking at the geology that you've got and sizing the system, designing the system to what it is in your specific area for your specific project. Like I say, a colleague of mine will be touching on ground collectors next week, so hopefully you'll get more information out of that if you tune into that. I think we're coming to the end now. So in terms of summary, you're looking at any building being able to be heated by a heat pump, but the design is critical. There's no reason why a heat pump cannot heat any building in the UK, and I think our case studies specifically prove that. Energy bills, you're looking to reduce those. That's one consideration for it, the same as carbon. Future-proofing your cut levels of comfort. Are there any subsidies available? And what might be best for the specific project that it is that you're trying to take on. I hope that has been relatively useful and sort of touched on all of the points that you were hoping to pick up on today and this morning. I understand that this talk will be going online, so you'll be able to find on YouTube, I think, this slideshow and take any notes down if you've missed anything. Of course, my contact details are here now on screen. So if you have any questions, please feel free you can write them now, or if they're more specific to a certain project, please feel free to get in touch either on the phone or via email. We've just had another question from Chris Kemp. That's more specific, I think, and the answer is yes. Yes, we can have that discussion. If you want to get in touch with me via email or phone later on today or next week, I'll be happy to have a chat with you about that. Any other questions? It looks like, I think that is doesn't look like we've got any other questions. So I think if you want to sign off, no problem. You're all very welcome. And if you do have any questions, please feel free to get in touch. Thanks a lot.